All right, so moving on from discussions of how frequencies are encoded in cochlea and how frequency affects our perception of loudness. I want to talk a little bit about audiograms, kind of getting into the applications of this science. So this I have found is not a common experience for Canadian students, unfortunately, but in the United States, everybody kind of goes through this as a kid. At some point, an audiologist comes to school and tests our hearing as students. And you may have had this experience just by going to an audiologist, anyways, for personal reasons or what have you. So, the way auditory test works or hearing test works is that you will sit sort of at a desk or something with a set of headphones on, and then the audiologist will play a series of tones to each ear independently. And if you hear a tone, you're supposed to raise your hand. Well, this is the right ear, I heard it there, and then left ear, I heard it there, so on and so forth. And the audiologist is kind of looking for the point at which you will respond to, like with 50% accuracy. They'll kind of reduce the intensity level of the tones they're playing to you until they get to a point where you hear it half the time, and half the time you don't seem to hear it or don't respond to it, basically. They play tones at different frequencies, and at each frequency they kind of reduce the intensity until they find that sort of threshold of your hearing. So they will then chart how much your hearing threshold differs from that of what's considered to be a normal listener, again, from those studies that were done way back when, at those specific frequencies they were playing the tones at in what's called an audiogram. So you can look at it here. These are how a particular listener responded to sine waves of the frequency 64, 128, going up by factors of 2, 256, so on and so forth, all the way up to 8,192 in this particular case. So the 0 level here is sort of the ideal case, and then anything different from that is either slightly better than the ideal case or slightly worse or maybe a lot worse. And the difference is measured in decibels. This is showing hearing loss in decibels. The circles are the response to the right ear, which is mostly better for most of this. Then it drops off at the high end, and the X's or crosses are the response of the left ear, which is generally worse than where it's supposed to be. So that's called an audiogram. So this gives you kind of a picture of how a particular person sort of processes the different frequencies at the different frequencies of sound or speech that human being is normally sensitive to. I've got a note here that noise-induced hearing loss tends to affect higher frequencies first, as we can see here. So again, those will be these sounds the base of the cochlea responds to best, or the cells at the base of the cochlea respond to best. And we have less cells devoted to, or fewer cells devoted to those frequencies to begin with, and we lose sensitivity to that range first. There's also kind of a phenomenon where people have a tendency to lose sensitivity around 4,000 hertz or so, kind of around that sweet spot of amplification that your ear canal will intensify as sound goes into your inner ear. Those sounds are kind of naturally going to be louder, the mid-range of frequencies, and we tend to lose that sensitivity first, I guess, through too much intensity coming into that part of our cochlea. As I mentioned before, if you do experience hearing loss at some particular range, you will lose that sensitivity for the rest of your life. Although they're working on some therapies for that, which can possibly make it better, and I'll show you how some devices work to help make that better as well. So I've got some examples here.
There are lots of huge buildings in Beijing.
Of these particular sentences.
Someone, somewhere, wants a letter from you.
I'll play those again, but these are the originals, and I'm going to play what they sound like with different sort of hearing loss audiogram curves applied to them.
There are lots of huge buildings in Beijing.
Someone, somewhere, wants a letter from you.
Okay, so if we listen to those two sentences with this sort of loudness curve plopped upon it, where we're losing about 15 decibels at 4,000 hertz and we're losing about 40 decibels at 8,000 hertz, they sound like this.
There are lots of huge buildings in Beijing.
Someone, somewhere wants a letter from you.
So that's a little subtle, but I think you can hear it, and you'll probably definitely hear the difference with these two guys where this left ear has experienced a more profound hearing loss at these higher frequencies.
There are lots of huge buildings in Beijing.
Someone, somewhere, wants a letter from you.
So that's starting to sound pretty muffled and not as intelligible, right? It's harder to pick up what is being said here exactly.
There are lots of huge buildings in Beijing.
And that is a replication of what the world sounds like if you have experienced hearing loss to some extent, at least according to sort of this model of how we hear. The sensitivity we have to higher frequencies also diminishes with age. This is known as presbycusis. And I've got audiograms here for people of different ages. So this is one for, 20-year-old is kind of this ideal case. Like I said, if you're in this class, you probably have ears that are working really well. Enjoy them while they last, because when you get up to 30, you start to lose some sensitivity to these higher frequencies.
Someone, somewhere, wants a letter from you.
At 40, it gets slightly worse.
Someone, somewhere, wants a letter from you.
And it keeps going.
Someone, somewhere, wants a letter from you.
At 60.
Someone, somewhere, wants a letter from you.
So a little bit less and less sensitive over time. So I know this is true of myself. I also had a bad habit when I was younger of, like I said, listening to music too loudly or even playing it too loudly. So I'm somewhere here in the mid-range, although I think I can still function, thankfully. There is also a phenomenon that I like to mention with respect to this. It's something that came up when I was first teaching this class about 15 years ago. It's a sound called the teen buzz. So this, as the story goes, was a sound that the store owners of 7-Elevens and convenience stores like that came up with because it was a sound that young people could hear. Young people like 20 years old or younger could hear, but people who are older, who were like running the store, could not hear, so it wouldn't bother them. But it was so annoying. It was supposed to drive away the young people from loitering on the sidewalk next to the 7-Eleven. I guess I'll just presume that kids still do that. I don't know. Either way, when you listen to this sound, it's incredibly annoying. And I'll give you a little sample here. It was also supposedly created to serve as like a ringtone back in the earlier days of cell phones. So it was supposed to be a ringtone that like students who had cell phones could hear, but their teacher would not. But again, when you hear this thing, you wonder why anybody would want to hear it at all. I can't hear it. I'm saying this on the basis of how students respond when I do actually play this in class over the loudspeakers. So it's basically just a super high frequency sound, like 16,000 hertz or so. And it has this interesting pattern superimposed on top of it, but the individual vibrations are very small. And you can see they're kind of jagged like this, and they go in that bigger curve. And so, each individual cycle of this is very, very short, less than a millisecond long. I'm going to play just a little snippet of this. Maybe I'll move out a bit. I can't hear this. I'm going to play it over the loudspeakers. It may or may not come through. Let's play it like that. We'll see how it goes. If you think this is going to be annoying to you, I'd recommend not listening to this. If you are curious and want to find out what it sounds like, you can go ahead and listen. But normally students kind of recoil when I do this. So here we go. Here's another one. Can you hear that? Maybe out a little bit. I can't hear that at all. Maybe you did. Maybe it was really annoying. I hope so, but I hope it wasn't too annoying that you want to drop the class. So that's what it sounds like, and we'll move on without me being aware of anybody cringing this time. So another problem with hearing that can emerge is what happens when you get an ear infection. This happens a lot with kids, and it's known as otitis media when you do get it. The otitis is just, this is the same root as bone in Latin, I believe. Like ossicles, otitis, so on and so forth. It's like an inflammation of those bones in the middle of your ear. So media means middle. But what happens is fluid fills the middle ear and kind of prevents those bones from vibrating in the way that they should. Remember at the beginning of this lecture, I talked about that eustachian tube, which connects the nasopharynx to your middle ear. So this is sort of like a similar sort of thing happens if you have, a cold and there's gunk in your nose. And then, if that eustachian tube opens up, like this has happened to me on planes when I've had cold and gone for a flight, is that gunk can get up in your middle ear and it's hard to get it out. But when it does, you don't hear things very well because those bones can vibrate. Same thing happens if there's just an infection and there's fluid that gets in there. So this leads to a form of what is called conduction deafness, in which the sound is simply not transmitted as well to the cochlea. And generally speaking, auditorily, frequencies from about 500 to 1,000 hertz will tend to drop out. This is what the audiogram looks like. In that particular case, there's like a bit of a notch down here in this range in terms of sensitivity. I've got a brief prot demo, which is not meant to be annoying, but you can take a token like this.
Someone, somewhere, wants a letter from you.
And we can filter it by removing, prot is set by default to have a stop filter, as it's called, that will stop the frequencies in this range from 500 to 1,000 hertz. This is maybe a little more extreme than what we actually get when we have this condition, but it would sound like this.
Someone, somewhere, wants a letter from you.
And maybe it's kind of funny to think that this might happen when somebody has a cold, because it kind of sounds a little bit like he has a cold.
Someone, somewhere, wants a letter from you.
But you can see this frequency dropping out here, like right around 500, between 500 and 1,000 hertz. So that's what losing sensitivity to those frequencies sounds like. I'm going to mention that there is a perceptual scale for loudness, like there are perceptual scales for frequency. And the perceived loudness of a sound can be measured in units called sones. And this is similar to what we saw for the MELD scale, where the sone scale exhibits a nonlinear relationship with respect to the absolute pressure values. So on the x-axis here, we've got absolute pressure in terms of air pressure rather than intensity, measured in what are called micropascals. And so this is in linear format. This corresponds to different intensities in decibels. And then over here on the left-hand side, we have sones. So the decibels are plotted in these black triangles here. And as you can see, that's a nonlinear relationship, so it jumps up really quickly at the low end and then it curves off towards the high end. Sones, what we saw with MELDs, is relatively linear here at the low end, and then it kind of starts curving off as we get up here. But it's not directly related to what the decibels are doing, is kind of the main point, or the actual air pressure values either. It gets bigger with greater pressures, but it's not exactly a linear scale. And that's all I'm going to say about sones, just so you know that our hearing system doesn't process those in an exactly straightforward manner either. Another scale for measuring auditory frequency emerged in the 60s. And this scale is a little complicated, like the origin of this is a little complicated to think about. It was derived from an experimental paradigm called auditory masking. And I have these demos that I put together. They don't work as well as I would like them to. But the idea is you could have what are called unmasked tones like this. These are low frequency. And they're getting quieter and quieter as I go there. But over on top of those unmasked tones, you can apply noise, like just white noise that you would get in an ideal case. And I've got different tones on the slide there, but I think it might be easier for you to see this in spectrogram form. So I've got just a pure tone here. And I'm going to change the spectrogram so we can see it in narrowband form. So it looks like this. We just have a very low frequency. And in fact, I'll change the spectrogram so we can see that jump out a little bit better, because this is very low. It's like 100 hertz or something. Yeah. So you can superimpose noise on top of that. And I'm going to, so this is just noise in general. Yeah, that's a little bit annoying. I'm sorry. But you can see the noise here. Maybe I'll change the spectrogram back because the noise kind of emerges better at the higher end. So the idea with this is that you can make the sine wave part of this quieter and quieter until you get to a point where you can't hear the sine wave above the noise. I tried it with this. This is kind of the most extreme example I've got, but I think you can still kind of hear the sine wave. And what they would do for this, developing this bark scale, is to filter out the noise. So let's see if we can do that. So we have a 100 hertz sine wave. Let's filter out all the noise above 1000 hertz for this one and see what that sounds like. Oh, that's interesting. I don't know if you can hear the sine wave there better or worse than before. We can tweak that so the range is even smaller. Yeah, let's go with this one and filter it from like 0 to 250 hertz. How about that? Yeah, that is kind of giving you a sense of what I'm getting at here. So this is what we started off with. It might be a little bit hard to hear that sine wave, not so much. It's not super easy to get it there, but there's a point at which the sine wave jumps out at you, and you kind of are not hearing the noise anymore. So ideally, you're supposed to get the noise to a point where you can't hear the sine wave, and then cut its bandwidth, reduce it to the point where at some point the sine wave will jump out at you. So the question they were looking at when they developed the scale was how narrow can we make the bandwidth of the noise before the sine wave becomes perceptible? And it turns out, interestingly enough, that the masking bandwidth is narrower at lower frequencies. So this inspired a scale which is called the critical band scale or the BARC scale. So using this methodology, researchers eventually determined that there were 24 critical bands of hearing. And the theory is that the auditory system basically integrates all acoustic energy within each band. So this is sort of like saying that there's might be different things going on within a specific range of frequencies in a sound from like 1000 to 2000 hertz, but your mind just kind of gloms it all together. It integrates it, like if you ever took calculus, it sort of like takes the integral and sort of just presents one sound to your brain. So anything that goes beyond that critical band will sound basically it'll kind of go into two different streams in your brain, but once you kind of get all noise within that, you're hearing only, one output of the system. So for example, two tones within the same critical band of frequencies could sound like one tone. Like critical band number 9, I'll show you all the scale in the next slide. That critical band will range from 920 to 1080 hertz. It's a bit of a stretch, but F1 and F2 for ah might merge together because they're often kind of in this general range of frequencies when they're produced as that vowel. So if they do, that might just sound like one formant to a listener rather than two separate formants. And often when we look at these formants in a spectrogram, they look like they're right next to each other anyways. It turns out, interestingly enough, so there are 24 critical bands of hearing, and each critical band corresponds more or less to about 0.9 millimeters on the basilar membrane. So what this means is, again, we have more of our basilar membrane devoted to lower frequency perception than higher frequency perception. So we're getting more critical bands at that lower end of the frequency scale than at the higher end of the frequency scale. Another way to think about this is that the auditory system consists of 24 bandpass filters, which are just responding to a range of frequencies within their bandwidth, and then the response to everything else on the tails just kind of diminishes considerably. And then each filter will correspond to one unit on what's called the BARC scale. So as promised, I'm going to show you kind of what this scale looks like, and it actually winds up looking fairly similar to our MELD scale, such that it is linear, or it has a more or less linear relationship with frequency at the low end, and then it tails off into a more logarithmic relationship at the high end. But instead of having hundreds or thousands of MELDs here, we just have 24 different BARCs, and these kind of define the limits of our auditory sensitivity. The frequency here is in kilohertz, so this is 1000 hertz, 2000 hertz, so on and so forth. I've got a fully defined scale here. So like I said, you have more sensitivity to these lower frequencies. So bark number 1 or band number 1 is centered around 50 hertz, and its bandwidth is from 20 to 100. They usually have a little more sensitivity on the higher end than the lower end in terms of bandwidth. Moving on up the scale, you go from like 150 to 250, so on and so forth. These are all going up by 100s, and then they start increasing by higher numbers in terms of their center frequencies, like 840 to 1000, 1000 to 1170, so on and so forth. Half of the scale is encompassed up into about 1600 hertz, and the rest is devoted to everything else, going up to like 15,500 hertz in terms of its bandwidth. So as before, more sensitivity at the lower end than at the higher end, but this is supposed to be sort of a more accurate representation of how the Audition system actually represents sound in terms of how it integrates energy within each one of these bands as it transmits that information to the brain. So the MELD scale is interesting because it shows us how we kind of perceive individual pitches in relationship to one another, but this is probably a better representation of how we represent complex sounds that we hear in speech or otherwise. So normally when people make an auditory transformation of frequency information in, say, phonetic studies, if you're trying to get a better auditory representation of what sound looks like to the mind, they will convert it into barks in phonetic studies. And they will do it using this scale or slightly more complicated math. I can show you kind of what it looks like when you do that. So this is a spectrum of the vowel schwa in both acoustic form and auditory form. So this is the acoustic representation here on the x-axis. This is showing what F1 looks like in the spectrum, and then F2 at 500 and 1500 hertz. What the bark scale will do for you is it will kind of expand these lower frequencies a lot more than we're used to looking at them in a spectrum or a spectrogram. So this is F1 for schwa, and it's not only kind of moved over to the right, but it's wider too than what we are seeing here in just the representation of the spectrum in terms of its harmonics. And this is F2 here, up around 10 or 12 barks. F1 is around 4 or 6 barks, so on and so forth. I've mentioned this before, but generally speaking with vowels, we care mostly about F1 and F2, and sometimes F3 comes into play, but these are kind of medial default values for F1 and F2, and you can see that they occupy about half of the auditory scale. So the other half of the auditory scale will be for whatever the other formants are doing. And this one as well can range, right, a little bit higher than that too. Because this is kind of the central value for F2. So like I said, auditorily, we start to lose sensitivity pretty quickly to formants above F2, which is why they're not normally important in language. You can also represent sound using the bark scale with what are called cochleograms. So these are spectrogram-like representations which incorporate these auditory transformations for pitch and loudness into a sort of spectrogram-like view of how sound changes over time. So these are a couple of examples I got from the textbook for this course of the Cantonese word gai, which I believe means chicken. It's like the only Cantonese word I know, but there you go. And kind of what you see here, I'll give you an example of how you can do this in Prot, but this is cheating a little bit because this shows a spectrogram in kind of a condensed way that we don't normally look at it, but this goes up to 10,000 hertz on the frequency scale. But this is our I diphthong here after a K release burst at the beginning. And we can look at this in cochleagram view, and we can kind of see the same curves of the first two formants. But you'll notice that F1 is a lot higher kind of than we're normally used to looking at it. There's a lot more space here to kind of see what F1 is going to do compared to a normal spectrogram. So I will show you how to make one of those really quickly. I've got some vowels here from Peter Ladefoged.
Heed, hid, haid, head, had, hard.
I'm going to change back to a wideband spectrogram so you can see the formants better.
Heed, hid, haid, head, had, hard.
And I will convert this thing into a cochlegram. I've done it before, but I want to do it so that you guys can see how it's done. So you go to Analyze Spectrum and say go to a cochleogram. Actually, before I do that, I'll point out, so you can go to a bark spectrogram or a MELD spectrogram, so on and so forth. Let's just go straight to Cochlegram, which also includes like the loudness transformation. And to do that, we actually have to, so it'll convert it to a Cochlegram for us. We can't view it in the normal way for some weird reason, but instead we can paint it. So there's always this kind of drawing window that emerges when you open up Prot, and we have never used it before. This is the one time we're going to use it. So with that highlighted, you can paint the Cochlegram in this window, and you can kind of see what look like formants in it. So I'll play this original without that spectrogram representation so you can kind of follow along. But like I said, it kind of expands the lower end of the frequency scale, so it's easier to see F1 distinctions. And to some extent, it's easier to see F2 too. But here we go.
Heed, hid, haid, head, had, hard.
Yeah, so with a lot of these higher vowels, they just have low F1, and we don't really see much action going on there in a spectrogram like down here. And this kind of helps exaggerate that. Basically with the implication that to our minds or to our ears, we're more sensitive to hearing these distinctions than we can normally see in spectrogram form, even though this gives us a nice representation of what's happening in physical external reality. This is what it looks like more in our brains. Because the cool thing about the cochlea is that it does a Fourier transformation on the signals that come into our ears. It's just not exactly the same sort of Fourier transform that we're used to looking at. Okay, I'm running out of natural light. I'm going to try to wrap up the fourth part of this before it gets too dark. So I'm going to stop now and talk a little bit about how we can help ourselves when our hearing systems don't work as well as they used to. Okay, see you in a minute.